Hello, this is Dr. Benjamin Norris from the Chemistry Department at Frostburg State University. Today, we're going to practice drawing organic structures using the principles of valence. Let's practice. For the formula below, use the principles of valence to draw a valid structure. I'm going to start a timer that has 10 seconds on it. If 10 seconds is not long enough to work out this problem, feel free to pause the video. Okay, let's see how to solve this problem. First, we want to take all of the atoms that are in the formula given and represent them with their typical valence. This formula has 3 carbon atoms, 7 hydrogen atoms, and 1 chlorine atom. The 3 carbon atoms are all tetravalent and can form up to 4 covalent bonds. The chlorine atom is monovalent, as are the 7 hydrogen atoms. They can all form 1 covalent bond. The next step is to assemble the multivalent atoms, those that can form more than 1 covalent bond, into a chain, and then see how many valence spots are left for the other atoms. In this case, we can form these 3 carbon atoms into a chain in one way, putting the 3 carbon atoms in order. We can also count that there are 8 remaining valence spots available, and there are 8 univalent atoms to attach. We're on track. However, you might start thinking, well, I've got this chlorine atom, and it can go in a lot of different spots. However, many of those spots are actually representing the same chlorine atom on the same carbon in the same compound. We won't get to the point where we can prove that for certain until we start understanding the nomenclature of organic compounds. So I'm going to ask you to take my word for it for a little while. It turns out that there are only 2 different ways to represent that chlorine atom. The first way is to put it on one of the end carbons, and we can fill in the rest of the hydrogens. Doing so generates the structure of 1-chloropropane. The chlorine can also be put on the middle carbon, and we can fill in the rest of the hydrogens to make 2-chloropropane. And in this case, these are the only 2 valid structures that match up with this formula. You shouldn't be surprised that there are 2 possible structures for this formula, given the fact that relatively simple formulas can generate multiple isomers. Let's do another practice problem. For the formula below, use the principles of valence to draw a valid structure, C3H6. Again, if 10 seconds is not long enough, feel free to pause the video. We approach this problem the same way we did the last one. First, we draw the atoms with their valences. There are 3 carbon atoms and 6 hydrogen atoms. Then we assemble the 3 carbon atoms into a chain, just like we did in the last problem. However, if you remember from the last problem, 3 carbon atoms in a chain have 8 open valence spots, and this time we only have 6 hydrogen atoms to put into those spots. 2 spots will be left unfilled. And when we have unfilled valence spots, we do not have a valid structure. One thing that we can do to account for unused valences is to tie them together. Now this little loop here might look silly, but what I'm actually doing is creating a covalent bond between those 2 spots, which creates a double bond between those 2 carbon atoms. Now we only have 6 open valences, which we can fill with the 6 hydrogen atoms. There is another way that we can fill in or occupy two valences, we can tie together a valence from carbon 1 and carbon 3. In other words, the carbon atoms at the ends of the chain. This doesn't form a double bond because those two carbon atoms were previously not bonded to each other. It forms a new single bond, wrapping this chain around into a ring. This ring now has 6 available valences, which we can fill in with the hydrogens. This is now another valid structure for this formula, and this formula happens to again have 2 valid structures. Let's do one more practice problem. For the formula below, use the principles of valence to draw a valid structure, C2H7N. Remember, if 10 seconds is not long enough, feel free to pause the video. We begin this problem like we did the last two. First, we write out all of the atoms and their valences. In this case, we have 2 carbon atoms and 1 nitrogen atom and 7 hydrogen atoms. The 2 carbon atoms are tetravalent, the nitrogen is trivalent, and the 7 hydrogen atoms are univalent. We then string the multivalent atoms together into a chain, which we can do by putting carbon and then nitrogen together. That leaves 7 available spots for 7 hydrogens. However, you might have noticed that there is another way that we can assemble carbon-carbon and nitrogen into a chain. The nitrogen atom, instead of being at the end of the chain, can be in the middle of the chain. This leaves 7 spots for hydrogens, and we can fill them in. And again, in this case, there are 2 isomers that can be drawn. Here's one final practice problem. This problem is a little bit different, and that there's not 2 valid structures that can be drawn from this formula. There are 10. And so rather than walk through forming each of them, after 10 seconds is up, I'll give you a summary of how to figure out the different ways that those atoms can be connected, and then I'll show you the 10 answers. Again, if 10 seconds is not long enough, feel free to pause the video. In this case, as in the last problem, there's more than one way that you can connect the multivalent atoms in this formula. You could form a chain of 3 carbon atoms and put the oxygen at the end of the chain. The oxygen could also be in the middle of the chain. Finally, the oxygen atom could come off of the middle carbon of the chain, producing a branch in the chain. These 3 different structures each have 8 available valence spots, and there are only 6 hydrogen atoms, so of course we will need to tie together some of the valence spots to make double bonds and rings. Because there are 3 different connectivities and the need to create multiple bonds, this is what leads to there being 10 possible isomers for this formula. I'm now going to reveal those 10 isomers for you, and I challenge you to work to try to figure out where each of them came from. There's so many of these isomers that in addition to representing 8 below the question, I have to represent 2 of them at the top. There are 1, 2, 3, 4, 5, 6, 7 isomers where the atoms are all connected in a chain, and there are 3 isomers where they are connected in a ring. In addition, there are a pair of isomers here that are stereoisomers of each other and not constitutional isomers of each other. Give yourself an extra kudos if you can find the stereoisomers. You might be looking at the structures on this page and feeling like the Lewis structure way of drawing organic molecules is starting to get a little bit busy, and it's hard to tell what's going on in a structure with all of these atoms taking up so much space. In an upcoming video, we're going to start learning how to represent these molecules using a simplified drawing mechanism that leaves the carbons and the hydrogens out so that the molecules look cleaner and easier to interpret. Thank you for watching.